So welcome friends to another episode in antennas. In this particular coverage I'm going to go through quite a number of antenna designs that span the early history of antenna development about 100 years ago. You might consider this as an exercise in first principles. That is where all antenna design has originated from, and through the various applications of what back then were called Hertzian and Marconi antennas. Hertzian being dipoles and Marconi's being monopoles, monopole being a simple vertical. So we're going to just dive right into it. Here we see a rather full description of the monopole, and it's a rather elaborate one in that it shows that it's an extension of a coaxial feed, or the structure itself is coaxial, as indeed shown in this structure over here. Either way, these are roughly similar in concept and construction. The principal element that we're interested in here is not so much the length or the height of the antenna. Often monopoles' lengths are described as height rather than the feed point height. So don't get confused by that. In particular, we're interested in the thickness of the radiator up here in this area. Each of these are described. You probably can't. Let me see if I can. Here we go. 20.6 degrees. 20.6 degrees. What does that mean? Well, 26 degrees is the thickness. That would be, well, let's just say that that's roughly a 1/12 of a wavelength thick. Well, let's call it a 1/10 of a wavelength thick. So again, let's zoom in again. Look at this structure in particular. Let's say that this is for a 10-meter monopole, fed at the bottom between this ground plane, which would be your radial system, and 1 degree above, or 1/360th of 10 meters, which would be, well, I'm not going to do the math in my head, but let's just say it a few inches, if that. However, the thickness of 20 degrees, 20.6, we'll call that a 1/10 of a wave, just to make math simple. For a 10-meter monopole, this A would be roughly 2.5 meters, and this would be 1 meter thick. So that's a pretty substantially thick monopole, 1 meter thick. Now in other coverage, I've described how this can be done in a cage design, which doesn't nearly bring such a unwieldy structure to you. But what's the implications of this thickness? Well, it all comes down to this figure here. The antenna resistance in ohms, we're going upwards to nearly 200 ohms here for the B condition. Well, what is the B condition? The B condition is roughly what we see here, this thick radiator. Down here in the A condition, we're seeing roughly 40 ohms of resistance, and actually 37 ohms when we're at the quarter wavelength, 90 degrees. Now 90 degrees out of 360, 1/4 of 10 meters, 2.5 meters tall. Not quite. It's not going to be 2.5 meters tall. That's the electrical length. That's not the physical length. The physical length is going to be slightly shorter, 5% shorter roughly. However, for that size monopole radiator, we can expect to see on the order of 37 ohms, or 40 ohms if you will. For the thicker radiator, well, it's not terribly much higher. Maybe double that. So you might want to consider that as we get to a higher antenna, verging on to a half-wave antenna, which would be out over here. We're looking in the numbers of a radiation resistance of, well, north of 160 ohms. And that can be a considerable advantage if you have a lossy ground system. So that's the first advantage of the monopole being thick. And now I'm going to probably skim through the rest of these pictures. This was just a short introduction to monopole thickness. And moving on, well, the next thing we can do to augment a monopole is to add a top hat to it. And in these illustrations, you'll see that this is carried out to the extreme, such that on the left we have a monopole above a circular ground. These are all cut in half views. Or a monopole with a top load disc over an infinite plane of metal. Both of these are they're very extreme, and if we look in, and there's no physical dimensions to any of these. We'll get into that in the next slide, which is this is how things should work. This is how things do work, and this goes back to the era of the this Marconi antenna. When Marconi was transmitting at the wavelength of 5,000 meters or 60 kilohertz, in this regimen, these towers were very tall, vastly taller than any ham, or not any, but certainly most hams have. No, 100-meter tall mast, and this isn't even 100 meters, this is several hundred meters tall. We can see that circular disc in the previous design is now turned into wires, a flat top, and frequently it's going to be more than 2 wires as shown here. It's going to be many wires to present a cage construction, but actually a flat sheet instead of anything complex. But still in all, a lot of wire up here to create this main capacitance as illustrated here against a ground field that's been installed below. Our transmitter is right down here. It has a loading coil to help with currents and to tune out these stray capacitances here, 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 and here. This is to improve the resistance, the current feed into a resistance that is unimaginably small. In this regimen, during the Marconi era, this was in the radiation resistance was in the terms of fractions of an ohm, fractions. In other words, your 10-meter monopole is 100 times more resistive. That is, it sees 100 times more radiation resistance than this one that you see here that was designed for 60 kilohertz. And in all practical terms, was built to magnify the currents through this flat top and this ground construction system. Of course, you can achieve similar gains over your own poor ground, but you're not going to be working at 60 kilohertz, let's just face that. So, moving on. Here we see the current distribution along a monopole as it's excited at either the bottom. This is an open end, it's saying that the bottom is insulated. And here we have a shunt-fed monopole that is fed through this system up here. It's just a sloping line down to a capacitor that's fed through coax from your ham shack transmitter right here. You'll see that the currents roughly in this region here are fairly almost identical, certainly at these upper portions. No current at the tip. That goes without saying. We don't show that this is a very high potential, and we'd have a cosine kind of relationship going down to a voltage that's beating at the bottom, whereas inducted by this loop here that's constructed. And you can see the current in that element is substantial, and this also affects the radiation pattern in becoming a secondary radiator to the main radiator. Moving on, this is a unique introduction to dipole antennas in that what we have here is an infinite sheet of metal with a oblong hole in it fed across these 2 points. In other words, this is open, this is just air, this is all metal, surrounded by air of course, and it's fed with a balanced feed. You can think of this as twin line at these 2 points. And this is a slot antenna, and it acts exactly like a horizontal antenna. So I don't expect that any amateur radio operator is going to erect this next to his ham shack. This is far more envisaged in the UHF and very high frequency bands. Here we have 2 capacitor antennas. Why are they called capacitors? Well, just as in the early monopole with the top load, the disc at the top, we've paired that. There's 2 pairs. The distance between them, the heights, the amount of plate area at each end, those are buried in the details that go with this graphic. But suffice it to say, this is early academic work in that I've never seen anything in this line out in the wild, so to speak. But it is a way of shortening the dipole, maintaining its launch characteristics, and maintaining its efficiency by ensuring that I2 or I1, the current in this branch, is sufficiently large enough to connect to the radiation resistance, which is still on the order of the standard dipole, or about 140 ohms. Here we have a folded dipole on the left and the folded monopole on the right. These particular designs are unique in that they're full length. In other words, this is a quarter wave tall, this is a half wave wide. Each of these wires, doubled back, form a very tight loop. This is, you might think of this as a loop. It's not a loop. This is not a loop antenna. This is a quarter wave antenna on the right and a half wave antenna on the left. And the wires are continuous and they're the same diameter, and they bring the added advantage of radiation resistance multiplication, in that what was formerly over here a 37 ohm radiation resistance, it has been now doubled to 140. This 140 has been doubled to 300, all by virtue of this extra loop introduced into the design. So this is one way of managing your feed point radiation resistance for a resonant antenna. This isn't going to work on shorter antennas, so make sure that you keep in mind this is quarter wave structures. When we go on, this reveals how, at the top left, we can see that we have our half-wave antenna, and it exhibits what's described as somewhere between 230 and 400 ohms of impedance. Let's zoom in on that. And we can see that the current directions are the same in all representations. Here we have 3 wires in parallel. One continuous and 2 definitely paralleled. This ups our radiation resistance another notch, upwards to 600 ohms. We can also do folds that are longer and use a 3/4 wavelength, and again we enjoy the multiplication of the radiation resistance. And this is just included for experimental for any height. So, moving on. Here we have the rhombic antenna. This is a horizontal antenna that has been extended for great length. And again, this comes from the era of long wave transmissions, but it's perfectly usable in the HF regimen. However, you want to be sure that this is built over a poor ground. And I know you can't control what your ground situation is. More than likely, it's poor. Unless you're in Iowa or the Midwest, where you're standing knee-deep in loam of corn country, wheat country, something like that, you're not going to experience any significant good ground situations. However, that might be available. But moving on. We're moving into the regimen of loop antennas now. Now, these are very unusual designs in that the lines are not all quite clear. It's a problem of reproduction, but you'll find the graphics in the book. This is from Shikolnikov. Shikolnikov. And what Shikolnikov was attempting to do was to maintain a constant current loop. Now, in a full wave loop, that isn't going to happen. That's going to have standing waves that vary between maximum current and minimum current. For this particular design, we want a omnidirectional loop antenna, much in the sense that a monopole is omnidirectional in the azimuth. Here, to accomplish this, we return the wire. We've returned the wire from the loop back in on the drive point. The wire goes out, comes back to the other side of the drive point. Similarly here, out from one end, in and back. These shorten the length of the wire. That's, well, not strictly speaking shortening the length, but certainly gives us a constant current over these lobes, which give us the omnidirectional antenna pattern that we seek from a loop. You might see some of these in modern constructions. We'll get into those later, but this is the historical perspective. Again, history has taught us that we can increase, particularly for receiving, we can increase the sensitivity of the antenna, the loop antenna. Again, this is a small loop. It's got a constant current through it, so it's not a large one. A large, again, would be a wavelength. Our standard square loops or circular loops in the amateur usage would be very large structures. These are small structures. And typically this is the style. This is a style of antenna that you might see in old movies sitting over the radio receiver in the living room. Those disappeared quickly, but back then they used multi-turn loops. Here's all the math for finding all the characteristics for that loop. Here's the loop viewed overhead, and how its radiation characteristics are viewed in this view. So what it's saying is this antenna is most sensitive off its ends, that end or that end. Here we find even more mathematics to solve various issues. This is to determine field strength. These are more designs. Some of them might be familiar in that now we've got this capacitor that's built in. It's still a multi-wire system, and I've got to say that over the progress of the years, most designs have devolved from these multi-turns to single turns. This one over here in particular shows that a shielded antenna. You might well ask, well, Richard, how well can a shielded antenna work? Well, it works by virtue of this opening right at the top. What this presents is a balanced shield. Ground is always visible to an antenna, and it's even more visible in this design right here. So it includes all the external connections to ground, the internal connections to ground, the shielding, and the balance, how the balance is achieved at this point by virtue of that connection, and at this point by virtue of this connection. More can be said, but not right now. We're moving on. Here we have two loops that are side to side or face to face, giving us characteristics such as this or this. These designs are probably not going to be found in the HF backyard antenna designs, but still they are available to you. These characteristics are going to vary somewhat from these these academic projections. But you'll notice at this point we have an inversion, a twist in the feed. So we're going to come on to that little twist in the feed. I think that's going to be coming up soon here. Yes, right here. This is the Adcock design, and you might see something like this in modern DFing, because these are the original direction finding antennas that were used in avionics 100 years ago. Well, slightly less than 100 years ago, back when they got radios into airplanes. What you see is this is quite obviously two vertical dipoles separated and fed with crossed transmission lines. That's what this element is all about here and here. These crossed transmission lines force phase relationships into the design that give us the characteristic sharp nulls that are so necessary for RDF. Now, each of these points can be abstracted into four separate and isolated monopoles arranged into a square pattern, much like you see at these points. And think of these elements being driven against ground through a transmission line that feeds ground at this point and feeds the elevated vertical at this point. We'll say that this is ground, and this is specifically talking about ground with this capacitance down here. We'll see more of this coming up. Here's various feeds that can be performed to achieve the same goals. And we're thinking of four elements, such as here, but here we see two element with a ground connection, two elements with ground connections. Each of these is going to see another pair with a similar feed arrangement, such that we can achieve this kind of balance, or imbalance as the case may be. So all of these vertical elements can be separated vertical radiators in your backyard. The distance between them is not critical at this point. We'll talk about that later because phase is very, very important. Here we have one of the original radio direction finder constructions, and what it is we have two static meaning immovable loops. Here's the first loop and here's the second loop. And this is in an isometric view, so think of it as a 3D kind of projection where we're looking at an angle down on this crossed loops. The only wire connections are those that we follow down through these 4 wires to these coils in this particular contrivance that's known as a goniometer. A goniometer has a rotatable coil within the field of these 4 axial aligned and 90-degree opposed coils. When you turn this coil, especially if it's aligned along these two points are going to be driven the most by the output, and these are going to be driven the least, being they're in phase quadrature. As shown here, we're no longer in phase quadrature, we're in the semi-quadrature where the field from this coil is feeding these 4 coils at various angles to cause this antenna system to be sensitive in this direction. If I turn this 90 degrees such that it's aligned in this axial, still causing all these coils to have induced currents from this rotor, then our field of sensitivity is in this direction, so 90 degrees. So as this turns, so does the field sensitivity, the directivity moves with it. So this is a variation of the Adcock right here, except that instead of 2 coils we have 5, and we're controlling the phase to each of these elements by turning this element here. This can be used to feed an Adcock design as easily, because if you notice, if we take out this element and this element, we have 4 verticals. The loops are not strictly necessary. They will impact the operation and the feed point characteristics, but we will still have the same radiation characteristics of the directionality rotating with the turn of this coil. In this particular, this is a half fishbone antenna. We've covered the fishbone before. I think it's the next, yeah. This is a pair of fishbone horizontal antennas in an array. This is the vertical. Okay, well, this is horizontally polarized. This is vertically polarized. And we're taking the feed from this these drops down here along this line, which is, okay, this is being covered up a little. We can see there's a termination at this end. The signal directions, this is basically a receive antenna. And you'll notice that at the bottom of each of these conductors, these are all conductors here, there's a 35 picofarad capacitance connection to the line that's running beneath it. So capacitor here, 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 and so on down the line. This is microfarads is the same as picofarads. We have specified distances, we have specified lengths. Certainly the overall length, 122 feet. This is going to be for probably the 10-meter antenna. Well, I'm not going to speculate. That's down in the weeds of the text that goes with this graphic. Okay, we've already visited that. Here we have what's called a Sturba array, and it's probably difficult to visualize, but what we have here is a quarter wave stacked with a half wave, stacked with a quarter wave. This is a stacked radiator. This is another stacked radiator. It's fed from a line here that splits between the two. And there's connections between the two radiators, again, with transmission lines at this point and transmission lines at this point that cross to create the phasing conditions that we want from this array. This is a vertical array, and it has a substantial gain. This is the dipole equivalent, and it's called, let's see, a pine tree array. So we have a number of dipoles, 1, 2, 3, 4, 4 behind, 4 deep behind. So 32 phased by these relationships at the transmissions lines. They're being crossed in this regard. So there's heavy transmission line application here to these phased array of dipole elements. And again, this is not probably going to appear in your backyard for HF, but you might reasonably apply it to, say, like Wi-Fi or Bluetooth. You'll find schemes like this abound in YouTube that mimic these kinds of large structures. This for a monopole, and this for a flat panel. And let's see, I think this is my final topic here, and this is traps. Traps for separating those vertical elements, where formerly we used transmission lines crossed going to the other radiator. Here in a monopole, we can use a quarter wave stub. Now, at HF, quarter wave stub elevated above another radiator and below a radiator is seemingly a physically complex task to achieve at HF. But again, you'll find something like this in the VHF, UHF regimens. Here we do it with a monopole and with a choke element developed by the internal structure of an open transmission line, which is each of these is equivalent to this lumped circuit of a tank circuit, capacitor and inductor. Or we may separate the two elements by an inductor of sufficiently a large reactance to separate the two, so that this acts independently of this, except through mutual inductance through the air. And this providing the additional length of this being too short in a different band. These are for multi-band or array constructions. So let's see, is that the last graphic? Yes. So we'll return to the ham shack, and that was a rapid paced introduction to quite a variety of antennas from 100 years ago. I've shown some of the current relationships that are exhibited specifically along a monopole, and those curves are first principles. You'll be going back to those curves over and over and over and over and over and over. It's something you can't escape for standing wave antennas, such as what you typically erect in your backyard. Traveling wave antennas being so immense and requiring so much real estate, I don't expect that. Those sometimes serve perfect field day opportunities where you're out in the field and you have a lot of real estate available to you. You don't have very tall supports, and you're on poor ground. Rhombics, long wires, infeds, they will all do well in this scenario. So I hope you find some utility to this survey of antennas. They'll be covered in vastly greater detail in following videos, believe me. I haven't even started. So 73 is all. Hope you enjoyed this.